Okay, so hear me out. What if I told you that you could fold space itself, punch a hole through the universe, and pop out on the other side of the galaxy whenever you wanted? That's what we call a wormhole. Today, we're going to talk about how you would actually make one. But it's extremely hard. Like, we don't even know if it's possible hard. But the physics is genuinely mind-blowing and surprisingly well established. Let's get into it. First, let's get on the same page. A wormhole is officially called an Einstein-Rosen bridge. It's a hypothetical tunnel connecting two separate points in space-time. Imagine you've got a piece of paper. Point A is one end, point B is the other. Normally, to get from A to B, you travel across the paper. But what if you fold the paper so that A and B are right next to each other, and then poke a hole through? That's a wormhole. The math? It works. Einstein and physicist Nathan Rosen first proposed it back in 1935. It falls right out of Einstein's equations of general relativity. But the problem is actually building one. That's what things get weird. Alright, so let's say you wanted to build a wormhole. Here's your shopping list. Item number 1, a singularity, or at least some extremely warped spacetime. Wormholes are predicted to form at the extreme ends of spacetime, like near black holes, or theoretically during the Big Bang. So, step 1, find yourself some insanely curved spacetime. Item 2, exotic matter. Here's a big one. Naturally forming wormholes, if they exist, would collapse almost instantly. They're wildly unstable. To hold one open long enough to actually use it, you'd need something called exotic matter. Well, what even is this exotic matter? It's matter with negative energy density. In other words, it doesn't just push spacetime, it pulls it in the opposite direction from normal gravity. It holds the throat of the wormhole open like a cosmic doorstep. But here's the thing, we've never actually found exotic matter in the quantities you need. We've observed tiny hints of negative energy effects, like the Casimir effect, where two metal plates placed incredibly close together experience a measurable negative energy between them. But scaling that up to wormhole size, we're talking almost incomprehensible amounts. Item number 3, extreme precision engineering. The geometry of a wormhole has to be perfect. Any instability and the whole thing collapses. Or worse, it becomes a one-way trip straight to oblivion. You'd need to precisely control the shape of spacetime itself. With technology we have right now, we can't even imagine that. So, is this just a sci-fi fantasy? But here's what's cool, it's serious science fiction. Physicists like Kip Thorne, yes, the guy who was a consultant on Interstellar, have done real peer-reviewed work on transversable wormholes. The theoretical framework exists, and we're not really making this up. But the challenge is energy. To hold a wormhole open, you'd need an amount of exotic energy that is, by current estimates, comparable to the mass energy of an entire star, but negative. In 2020, researchers at Caltech proposed a new type of wormhole based on quantum entanglement, a concept called ER equals EPR. The idea is that two entangled particles might actually be connected by a microscopic wormhole at the quantum level. It's wild and theoretical, but it suggests that wormholes might be more embedded in the fabric of reality than we thought. Oh, and here's also a fun bonus. Wormholes might allow time travel. If you took one end of a wormhole and accelerated it near to the speed of light, and then brought it back, time dilation would mean that the two ends are now at different points of time. Step through one and come out in the past, or maybe even the future. Physicist Stephen Hawking famously argued this proves wormholes can't exist, because if time travel were possible, we'd have tourists from the future showing up. The absence of time tourists, he said, is evidence that they never got built. So, can you build a wormhole? In theory, yes, the math allows it, but in practice we would need exotic matter that we've never found, energy on a stellar scale, and engineering precision that would make our best technology look like a plastic spoon. But here's the thing about physics. What's impossible today has a funny habit of becoming merely very difficult tomorrow. 100 years ago, the idea of splitting an atom was a fantasy. 50 years ago, putting a computer in your pocket was absurd. Wormholes might be the next frontier, or they might remain forever in the realm of equations and imagination. Either way, they're incredibly cool. If you guys enjoyed this video, make sure to like and subscribe. Be curious like a child, the world needs more of it. Bye!